Yes, it works. Yeah, thank you for having me here talking about weather and climate data. And as was just mentioned, I worked as a climate scientist for many years, and since a year ago I swapped over, and now I work for the IBM Watson Data Platform, where I work as a developer advocate, which means I get to play with everything that IBM develops and get to test it and tell people about it, and also have an opinion about it, which is also allowed to talk about that kind of things. This talk, I want to talk obviously about weather and climate, and I'm just going to slowly go through what you could do with it, data formats, how it works, and as it says, beginner's guide, it won't be too hard to follow at all, I think. It's basically how to get started. And my slides, well, they were supposed to be there, but they will be on SlideShare after this talk. I'll put them up later. I kind of forgot to do it ahead of time. And this is where I wanted to start, because obviously everyone uses this, uses the weather forecast on their phone. And where does it come from? How does it work? Where do you get the data from? Things like that. So I wanted to start with a quick demo, actually, in a notebook, in a Python notebook, because all my examples will be in Python, which is my language of choice. I try to use others, but just seem to get back to it all the time, really. And I'm going to do this all live, so let's see what happens. And for this, I'm going to use something you can't see. Right. I'm sorry about that. I know. That worked now. So yes, there it is. I'm going to use the data science experience, which came out like a year ago, which is basically a way to do data science in the cloud. So it gives you a place to share and work together on different projects. And I just wanted to quickly show you how I'm going to run this project. Really? Anyway, if you go in there, you get into a list of projects that you can work together with people on the same notebooks, Python notebooks. And I wanted to click you through to get there here, but anyway, here we are in a weather forecast notebook, which is basically just a Python notebook, which is a great way to do data science, I find, because you get to work. You can combine basically bits of comments in Markdown, which is this bit, the top bit at the top, which is this Markdown, which nicely formats if you run the cell, and then combine it with bits of code. And I have run a little bit of it already because it takes a bit of time. But basically, to get the weather data out, you use an API, which is not that surprising, obviously. But first, I need to get to know the location and my current location to get a weather forecast out, obviously. And in Python, I couldn't find a function for that, so there's this nice, easy thing to use, which is the JavaScript Magic, which means you can use different languages within your Python notebook. So in this case, I just looked up the geolocation for this location where we are now. It takes a while to execute, so that's why I did it before. And then it gives you the latitude and longitude back into Python. So we've got the latitude, longitude now. Then these are the credentials for the API, which I got through Bluemix, which is IBM as well. But you use any API you want, obviously. And then, yeah, do a request, and you get a JSON file back with the data, which is, in this case, this file. So here you get a forecast for the next 10 days back, which is what I requested here. This is from Bluemix, from the weather company. There's a few really simple APIs within Bluemix, and if you're like a serious business user, you can go to the weather company directly, and they have many more. And well, this is the JSON file, so it gives you a forecast with all the information and temperature, wind direction, whatever you're looking for. And obviously this is not the easiest format, so I have to convert this one into, in this case, I converted it into a pandas data frame. And I have put these notebooks all on GitHub, so I'm going racing through it now, but just to give you an idea how I did it. But you can go back to the code, converted also the time into a date time format, so it's usable, threw away all the things I don't want, and then changed some data types to numeric, so I can actually plot it. There was something wrong with the data, and now I have like a nice table with the wind speed, relative humidity, cloudiness, and temperature, etc. for different dates. And it's pretty easy now. You got your data. Oh, this is the same, don't know why. And plot this with matplotlib, for instance. So you just make two subplots and plot the whole thing out in a bar chart for rain, because it looks nicer, or temperature. And the other thing that's quite easy to do now, because this API is pretty fast, I'm running it now over loads of cities in the UK, saving the temperature into a data frame again. And then I get a data frame for each city, latitude, longitude, and temperature. Which then again, there's a purpose why I'm not showing this code to you. I'll come back to that in a second. But obviously you need quite a lot of matplotlib code to get these maps out. I got a very retro map of the UK here with the current weather, basically. So it's 11 degrees, I think, now in London. But there's a way cooler thing to do this, which people in my team have been working on, which is called Pixie Dust, which is a package for Python, which basically makes it a lot easier to do all these kinds of visualizations. And especially if you're new to Python and new to code, I remember matplotlib took me ages to understand how to work with, and especially making the maps. So this is easy. You just say, display your data frame, and it takes off. And it gives you a figure, just like that, really. And the only thing I have to do here, I can also have a look at the data itself. So it gives you a table, the schema, so what's actually in there. Then I can choose a chart that I want to plot. In this case, I wanted to look at a line chart. And then there's lots of buttons to click, which parameters I wanted to look at. So in this case, I want to look at the date and temperature and rainfall. And then the two subplots. And it's very much in development, because 2 weeks ago there was no capability for time series, but we put that in because I needed it for this talk, basically. So it's a really fun and interesting thing to do. And a colleague of mine did also play around with maps. So that's invisible now. But basically, it uses a lot of HTML and JavaScript in the background to use, in this case, this was Mapbox renderer, but you can also choose to go for a Google, and if you're really interested in this kind of thing, go and help out and add more, because we're really just started to make this all look better, and the visualizations do need a bit of work, I would say, as well. And in this case, just the same kind of menu pops up, where you can just choose your variables, latitude, longitude, obviously, and a temperature value. And for this one, for Mapbox, you need an access token, which is free, but you just have to sign up for it, and then you can run these kind of things. And I just realized this might only work if you're connected to the internet, but that's just something I just realized right now. I haven't tried it out. Might not work if you run it locally with no internet. So this is kind of a cool way to get started with weather and get to know the data and start playing with it, I think. There's lots of variables. This was obviously very basic. So I think I went, no, I didn't. The data I used came from Bluemix, which is basically the big box for everything that IBM has on offer is available, and you can also try it out. And if you don't use it a lot, it's pretty much free at the moment, I think. And I also used the data science experience, which are the links to here, just to keep the whole story together, to give you a note. And Pixie Dust is the other thing I used, which is open source. It's all on GitHub, the code, and we have a lot of, if you have anything you want to add or do, just send a request there, and normally gets picked up really quick at the moment, and which you can just install in your notebook straight away using pip install. So this is a nice environment. Now you have to know hardly anything about the Python yet. You can just say display and go and have a play with the data. Also, but I wanted to talk a little bit more about where the data comes from as well, of course, because what I just showed you, that was a forecast, so that clearly comes from a model. And then there's also observations. So I wanted to talk a little bit about these two kinds of data that are available and where you can get them from. And I had a look around at the Met Office website, and they had this nice map there where they said, well, we measure everywhere. Here we measure temperature, humidity, wind speed, air pressure, rainfall, radiation. And then I looked a bit further, and then they say, actually, you can download the data from these points only. So at the link at the top, you can just go and download the time series for these points, and some other links where you can get data from. I know there's way more, but this was just a few that I just thought of quickly. And the second one is, of course, the weather company one, which I kind of had to mention now. And the third one is a really cool product, I think, is the Climate Explorer from KNMI, which is the Dutch weather office, which is a very interactive way to find data. But it's not only observations. You can also look at the different model runs for the different, from the different large climate models around the world that have been run into scenarios and go into the next century. So, and you can start comparing them and download all this data, which is quite cool, or even just analyze inside the tool. And the last one is the CREW dataset, which is where they basically take all the observations around the world of temperature and rainfall, I think, and they combine them together and make them into global maps. And obviously there's a lot of debate, or has been, about how they do that and if this is correct, and et cetera, et cetera. And that's basically what I want to talk about a second. Is that readable, the pink? I can't, okay. But basically, what I thought, you have like all these nice points, but I actually want a map, or I want data where I want to know the temperature where it's not measured. So it is pretty easy to do this. So you basically have a problem where you have just a few points of data. In this case, I tried drawing it. So you have a few points, which happen to be really nice and easy. It's really easy to just draw the lines in between by eye, but it's also pretty easy to do this in Python. There's a nice package for this, which is inside the SciPy Interpolate. It's called grid data, and it basically, in this example, I used the points from the map I showed before. So I just have a few temperature points. The only thing you have to do is define a grid of latitude, longitude, which are the x and the y, and turn that into a two-dimensional arrays, two of them actually. Then put the latitude, longitude, and temperature into a matrix as well, separately. And then you say grid data, choose a method, and then plot it with cont2f at the bottom. I'm going quick again, but this is basically what it does. So it gives you, from the points, from the map, gives you the temperature over the UK everywhere. Clearly, the nearest method does not work at all, because it just chooses the temperature that's closest to you, which I would say doesn't work with this continuous data at all. But it's a way. The Lillian one just tries for each point in between the other ones. It just interpolates linearly, so it does not look that nice. And then the one on the right is the cubic one, so it's like a cubic equation, which starts to look a little bit nicer. And there's obviously way more advanced methods. Like kriging is a method where they really try to find the most smooth way to go through all the different points, and which works real well. So that's basically, you go from point to maps, which is not that hard, but that's what I did also on a global scale to come up with the global maps. I'm sure they didn't use this, they use probably something better. So, and then the other thing, you have all these maps, and obviously you can't, it's not really a good idea to start storing them into CSV files because, well, it doesn't really make a lot of sense, I would say. They're gridded data sets. For that, they have a nice data format actually, binary format, netcdf, which basically makes you define a latitude and longitude and then as many grids on top of each other as you want. And was a bit of a giveaway. I am now gonna just, oh, that's all right. Run this locally because, as I said before, it is just as easy in many cases to run these notebooks locally than it is on the cloud. It seems to be more difficult today even. I don't know why. Yeah, there the kernel is back. So in this case, I need a package called netcdf, obviously, and NumPy to play around a little bit with the data. And in this case, I downloaded just a crude data set, which is the temperature anomalies over the last, since 1850 basically. So for each month, you have a change in the temperature anomaly. And I downloaded it and stored it locally. Really easy. You can just now load this file. It's a .nc file. Okay. It's a data set which has some variables attached to it. So I know now it's a netcdf model in this case. The variables, so what's actually in the file, it will tell you that. So it has a latitude, a longitude, and of course there's a temperature in there somewhere. That's a lot. But then you can just quite easily get all these things out. Also get a timeout, convert that into something readable and not, I think it's seconds since 1850. And then you have several arrays. So we have a longitude, which is just 72, latitude is 36. So this, because this is a 5 by 5 degrees global grid. And then we have 2006 grids for each month over the last 160 years, a bit more. And then obviously it's really easy, again, to plot a map out of this. This does not exist yet in Pixie Dust. It doesn't do anything with grids, only with points. So I'm going to try to run this. And it does work. I do know what went wrong actually. I've forgotten to put it in matplot in, but I showed you already. And then you can of course save it quite easily back into a netcdf file. So if you create your own gridded data, create the dimensions, create the variables, and save it basically. And that map that I just showed went actually wrong. That was the whole, because it was upside down, and which seems to happen all the time when you work with this kind of data, because different climate institutions, they seem to have different ways of storing things. So when you try to compare models from different models, then you also always end up spending weeks turning maps upside down and things like that. That seems to be always the case. But anyway, it does look like that if you do it right. So that's why I put it here. And that's the other type of data that's nice, but this was all based on observations. So now forecasts and predictions obviously are different because you need a model to do this. And I'm going to explain climate models with one slide, which I don't think is actually possible. But this is a climate model, very schematic obviously. What it does, you have a grid of the atmosphere, and for each of these grid cells, there's a lot of the water momentum, temperature, all these balances are being calculated using a lot of physics equations. And then there's a few boundary conditions that contain the atmospheric box, which are the ocean, which has exchange of heat and CO2. The vegetation, which I spent 10 years of my life on trying to understand how to put that into the models and how to parameterize that. And then, of course, there's the top of the atmosphere. And that's basically it. So that's how you need to solve this. You have an initial condition, you start running the model, and of course and then the whole climate research is about how do we do this best? What grid size do we choose? What's the best? How do we represent clouds? What's the parameters? Vegetation. What do we need to know about this to make it all work? Do we need the ocean? How does it interact? Etc. etc. So that's all of climate research in 1 minute. Don't know if that was a good idea, but things you could then do with these models are quite interesting. This is what I've been working on a bit, which is then take one model. This was an older version of the Met Office model, I think, and just run it into the future. So it goes from 1900 to 2100, and see what happens if you change the parameter values in the model. So you change, in the red ones, the parameters of the clouds, so the albedo of the clouds and how quick the rainfall is. Condensation of the rainfall in the air, when it's snow, when it's rain, things like that. Or you look at the carbon cycle, which is the red one. So here you change the albedo of the vegetation. You change how much the forest, how fast the forest takes up carbon or how it transpires, things like that. And the other one is all about the ocean. And then if you just change all this, just the parameters in the model, and you keep everything exactly the same, and you run these models, these will actually had to be run in the Met Office on the supercomputer, because they take ages to run, really. Then you see a massive variation, just uncertainty in the model based on the parameters. And this is an interesting thing to look at, try to understand why and how and which one is actually best. And that you can do, of course, with observational data going back in the past. And another thing is that you could do with these kind of models. You take just one model again, and then you only change one thing at a time. So if you, for instance, want to understand the increase in global temperature, which they have really nice graphics on this website about, which I kind of borrowed to make this point. It shows quite nicely, you can see how, you can just try to figure out why temperature increased. So in one case, you only change one of these. So that's very small. So you keep everything constant. So there's no CO2 increase, there's no solar cycle, there's no volcanic eruptions, nothing. And then you start changing them one by one and see what the temperature increases does. So if you do, for instance, the black one is the observed temperature increase. In this case, it's from a model, but it followed the observations very closely. And then you change all the natural factors and keep all the human factors constant. You see that this doesn't match up, for instance. And then if you start playing around with adding more different factors and trying to figure out which one is actually doing this, then it is pretty obvious in this case that the temperature increase was due to the humans. And this is just a summary of all these different ones, but it's mainly the greenhouse gases. And you can download that data and have a play around and put actually some real statistics to it. And then the last thing I wanted to talk about, this is all a bit like, where does the data come from, how does models work, things like that. What to use the data for yourself. I think there's a lot of things you could use it for. Obviously, it is used a lot already in insurance. Energy companies use it to, for instance, predict how much solar power they will generate, how much wind power, or when it gets real cold, how much energy will actually be used by the households, things like that. And in retail, they use this to predict when to put what on the shelves in the stores. So, for instance, do we need to buy a lot of barbecue, sell a lot of barbecue meat, or when are the strawberries out, things like that. And so yeah, there's a lot of things you could do, and I had this brilliant idea to come up with a really big example here, but it was more hard than I thought. I'll give you the start of what I did, but the interesting thing is there's a lot of things related to weather, obviously. And the example I wanted to show is using traffic collision data in New York, which is a very nice city, which is a data set which is updated daily, and it gives you, since 2014, all the traffic collisions. So it gives where the latitude, longitude, and it also gives you how many persons were injured or killed, or cyclists or motorists, what was the reason for the collision, and what vehicles were involved. And it was a bit more than 1 million lines, this data, and after I cleaned it up a bit, I ended up with a bit over 800,000 collisions that I wanted to see if they had anything to do with the weather. And as always, I was very optimistic. Just thought, I'll just code this up and it will work. And then I just ran into 1 million problems, which always seems to happen. And anyway, these are just, it's just a map. I actually stole this from a colleague because he wrote a notebook about this that also uses this data and does a bit of statistics on it. And my idea was basically, okay, I have all these collisions. I have an API, I'm just going to do 800,000 API calls. I thought that's just silly because I don't even know if there's an effect. So let me just first look if there's actually a difference in temperature or in weather over New York during the time. So I might just be able to use one data set. So I just divided them up into 5 boroughs you saw. And I looked at the temperature for the last month. And the different colors are just the different areas in New York. And they're kind of following each other close enough, I thought, because I had these 5 time series now anyway, to just split them up in 5 time series. And yeah, that's where I ended, because then I thought, oh yeah, I'm just going to add this together, this data set, and it made absolutely no sense. Because it's quite easy to join it together on date. You can just merge 2 data sets together, and then I thought, well, that's really nice, but I have now a totally useless data set where I have I know the weather, I know the collision, but I need to actually convert this data in nice time series per day. What's the weather, how many collisions, etc., etc. So that's where I was yesterday, and because I thought it would just work, and it didn't. That's what I'm going to put on GitHub, probably over the weekend, because I was really annoyed at myself, because I thought it's just going to have a nice data set that will easily follow out of it, and it didn't. But the idea, obviously, is I forgot to summarize the data and have a nice look at the daily weather data and how many collisions, and can I then do any statistics and then build a machine learning model with the observed weather over the last 4 years, and then predict the collisions for next week. That was basically my plan. I think it's still very doable. It isn't too hard, but I just didn't give myself enough time to do this. That was basically what happened. I still hope I give you a bit of a summary of weather data, how it comes, in which flavors. It comes in JSON files, time series, obviously, in maps and gridded data sets, which I didn't show that, but you can then, of course, aggregate back to time series. So that's what I've been doing, working in climate research, is basically moving data around a lot from time series to maps and back, and to aggregate it again, and then go for hourly measurements, and then I decide, oh, I need annual now, and I think and the units are always wrong. So that's basically most of the life of anyone who works in climate research, is doing these kind of things. And then, of course, there was the models, which is quite interesting, but also a very challenging problem and never ending. And that was a bit of an example that I wanted to show you. And the big thing I still want to mention again is Pixie Dust, go use it, have a play, because I think it's real cool. It's in development, and we're adding something different, new to it now. It's called Pixie Apps, which makes it possible to make live dashboards within your Python notebook. So it makes it really easy to combine JavaScript of HTML and CSS and to make it all really interactive with buttons and things like that. But it does work already. We're just working at the moment at examples and how to make it really work and to get rid of all the bugs, basically. A bit of references of Bluemix, which is where you can find the API, data science experience, as I mentioned, Pixie Dust, my slides, and the notebooks. Some of them are already on GitHub, some not. And at the bottom, me, if you have any questions or things like that. And the last thing I wanted to mention, a colleague of mine is organizing this. It's a machine learning for the search for extraterrestrial intelligence hackathon. Well, basically, it's a machine learning for SATI hackathon. He is a physicist and he also works for IBM at the moment, and he has put a lot of data together in a very clever way, I think. Don't know exactly, but it's now ready for people to play around with, and it is all freely available, and this is where you can sign up. I know it's very far away in San Francisco, but at the same time there's also a code challenge going on, so there's a Slack channel that people are getting really quite active in, discussing the code and the data and what you can do with it. Because I had a play and it's really interesting, but I did not figure out yet what to do with it and how it works, but you might be able to do this. Thank you.
Great, thanks Margriet. We'll try and make sure that we can get those references because there's a lot of really interesting stuff in there.
Yes.
We'll get that onto the website for this festival, so people who didn't manage to get snapshots of the screen as they were going through can go there and have a look for the details. Does anybody want to ask some questions? I'll bring the mic down.
Hello. As far as I understand, the modern predicting algorithms in physics, are based on some complex equations in physics.
Sorry, I can't. It's very difficult to hear.
Is it? Oh, is it better now?
Yeah.
Because as far as I understand, the prediction models and are based heavily on equations in physics, which are really complex and take ages to calculate on the supercomputers, as you mentioned. Do you think that there's any room for machine learning in terms of predicting weather? Because as far as I'm concerned, the process is inherently chaotic and it's really hard to make any reliable predictions. Do you think machine learning can help or can add anything on top of the current models?
Yes, I definitely think so. And there's quite a bit of research going on where they just take lots and lots of different models which have different initial conditions, and then the rest stays the same, and then they go in every single direction, which basically shows the chaotic bits of the model, and then use the output of these models to try to understand the whole behavior of that with a simpler model. And there's names for this kind of work, which I've completely forgotten at the moment. But yes, that's been done, trying to make you classification models and things like that based on the very complex physics models.
Just to sort of follow up on that, actually, for those who are trying to do this at home, as it were, do you have a sort of suggestion for the sort of scale of data we should look at? Should we be looking at hourly data and monthly, daily? If you're downloading a data set to just play with, do you recommend, what sort of level of sampling do you recommend?
I normally look at monthly data because that gets you a little bit of a nice seasonal cycle, but of course you lose a lot at the same time as well. But the data I showed, the global map, that is all monthly. And I actually forgot to put that in the slides, but you can also just actually run the climate models yourself through climateprediction.net, which my postdoc was around it and I completely forgot to put it in. But that's a way to contribute. So use your machine or your computer at home to run climate models, which then send back. So one of the models that you could run then yourself will just have a different set of parameters and then will be part of a very, very large experiment where 1,000 and thousands of models are being compared and then analyzed.
So now you become a data scientist yourself, I suppose. So how do you think about the disruption brought by data science to climate science? Do we just forget about the model we have built for the last decades or even centuries about how we climate change, how the climate change, and using data science, using machine learning, simply we more or less we forget everything. And then you put the data into the computer and ask whether you can make a prediction. But what we have learned, we have just forgotten it. How do you think about this thing?
No, we're definitely not throwing the physics away, because that is actually still the interesting part, and there's so much to do there and to improve. But adding like all the statistics and the machine learning on top of that gives like an extra layer of information. So it's a nice thing to combine. Still do all the physics, obviously, because it's really hard, and especially on the atmospheric level and going on different sizes of the grid. If you go real small, you get totally new, different problems because, well, you have different processes suddenly being important. And as the computers get better, you do go to a smaller and smaller grid, and then you still need to parameterize and understand the system again and try to understand that in a way. So I think they go really together. It's not throw away the physics and do stats.
Any other questions down there?
Yeah, maybe just to add to the previous question. So I think the way to see it is as you increase resolution, you can actually do more physics, because then it becomes meaningful. Whereas if you, at the current global scale models, you can't, for instance, use physics to compute stuff like cloud cover because the resolution isn't high enough. But if you go to smaller areas or you go to high resolutions, so you can afford to go to high resolutions, you can actually use physics to do that. So that's sort of the holy grail, but is this even on?
Yeah.
Okay. So yeah, I think there's still a way to go to that. I had a few questions and comments. In your example, you used NetCDF. Have you come across Xarray?
Sorry?
Have you used Xarray?
No. Oh, in the
Yeah.
Python code, you mean?
Yeah.
I think I did.
What's your experience with it?
Okay, I don't know.
Oh, you haven't used it?
No, I don't think
Okay.
so, no.
So that might be something useful. I work for an institution called the European Centre for Meteor Managed Weather Forecast, which is sort of so we do global weather predictions, and we also have the world's largest climate archive. So if you want to do sort of climate research and you want to get your hands on a lot of data, then you can basically some of our data is publicly available, so you can just go to ecmwf.int and you go to our public data sets, and you just need to create an account and accept the terms and conditions, and then you can download quite a lot of data. Just if you're interested.
Yeah.
Great, thanks. We'll try and make sure we get that address onto the slides,
Yes.
just as another reference. Any other questions? No? Looks like it. Let's just take the opportunity to thank Margriet again.